Hello, this is Dr. Hanaa Assil, and this is Unit 4 of June 2023. This is in the Pearson Edexcel International A-Level for Chemistry. So let us take a look at the questions and discuss the answers. The first question here says a homogeneous equilibrium is shown. What is the Kc for this equilibrium? How do we write the expression for Kc? Remember that Kc means concentration of products raised to the power of their coefficients divided by the concentration of reactants raised to the power of their coefficients. So here, of course, the products are 2y plus z, so the Kc would be concentration of y to the power 2, concentration of z, over concentration of W times concentration of X. The reaction shown occurs at 360 degrees Celsius, 1 atmosphere, and we have this equation. And it says that the delta H for the forward reaction is negative. Remember, if the delta H for the forward reaction is negative, that means the forward reaction is exothermic. Now, the question is, what is the type of equilibrium and how is the Kc affected by increase in temperature? So, let's take a look at type of equilibrium. Is it heterogeneous or homogeneous? Remember, heterogeneous means there are different states of reactants and products. They have different states. If it's homogeneous, then all of them have the same state. So, here we have carbon monoxide, water at 360, remember water at 360 degrees Celsius is in which state? All of these are gases. Carbon dioxide is a gas, hydrogen is a gas, all of them are gases, and that means this is a homogeneous equilibrium. So my answer is B or D. Now, what happens if we increase temperature? Again, remember, when we increase temperature, the reaction goes to the side that is endothermic. If the forward is exo, then the backward is endo, and that means when I increase temperature, this reaction goes backward. Now, when it goes backward, this is the expression for the Kc. And if it goes backward, that means I will have less CO2, less H2, and more of the reactants, and that means what would happen to the Kc? Of course, if we go backward, then the Kc would decrease. Following? Okay. What are the units of Kp? First of all, how do we write Kp? The expression for Kp again is partial pressure of products raised to their coefficients over partial pressure of reactants. So the Kp for this equation is the partial pressure of ammonia raised to the power 2 over the partial pressure of nitrogen times the partial pressure of hydrogen to the power 3. Each partial pressure is in atmospheres. So if we put in the units for each of these, then the overall unit, remember we cancel whatever is the same up and down, and we write what is left. So what is left is the atmosphere to the power of -2. High performance liquid chromatography, HPLC, is used to separate a mixture into 3 components, and this is the resulting chromatogram. What is correct for the labels on the axis? Okay, let's remind ourselves. What is high performance liquid chromatography? Remember, high performance liquid chromatography is a method to separate the components. In this case, we have a stationary phase. In each of the chromatography methods, we have a stationary phase and a mobile phase. Now, for the HPLC, the stationary phase is a non-volatile liquid, long-chain hydrocarbon liquid on a solid support such as small pieces of silica. So we have a column in which we have silica with a stationary phase adsorbed on it, and we're passing through this column, we're passing a mobile phase, a liquid. So this is what we call the HPLC. Now the chromatogram that we have, first of all, the question is asking what is the labels of these axes. Well, as we pass the mobile phase through the column, some of these components will be more adsorbed to the stationary phase, so they will take longer time to go through. So this is actually a graph of time in seconds versus the absorption. So as we go down, the substance that takes more time to go through means it is more adsorbed to the stationary phase and less into the mobile phase. If it goes out very quickly, then it is more attracted to the mobile phase. So in this chromatogram, the x-axis is the time, the y-axis is absorption. Now, which is correct for the components? Which one is more attracted to the stationary? So the one that is more attracted to the stationary, we said, is the one that will take longer time to go through. If it's attracted to the stationary, then the liquid mobile phase will not take it quickly. So it will take longer time. We say it takes longer retention time. So the one that is most attracted to the stationary phase is G. Now, which one is most abundant? Remember that the absorption for each of these is related to how much of it I have. So if F has a higher peak, that means it is the most abundant. Which pair of compounds can form a racemic mixture when mixed? What do we mean by a racemic mixture? A racemic mixture means a mixture of equal amounts of two optical isomers that are mirror images of each other. So first of all, I need two different isomers. They have to be mirror images of each other, and if they're present in equal amounts, then they form a racemic mixture. So which of these, if you look at all of these, the only one that is a racemic mixture is this one. Can you see that these two are mirror images of each other? If I have a mirror in the middle, then what is on the right is a mirror image of what's on the left, and that means these will form a racemic mixture. The others will not form. They are either the same compound or they're not isomers in the first place. So these are the only possible answers. Okay, question 6 says this compound is a drug used to treat heart problems and its structure is shown. How many chiral centers are there in this molecule? First of all, what is a chiral center? A chiral center is a carbon that is attached to 4 different groups, or it is bonded to 4 different groups. Then it is a chiral center. So which of these are chiral centers? Look at the compound. You'll find that this is the only carbon in the molecule that is attached to 4 different groups. So it's attached to an OH, and of course there is a hydrogen that is not drawn there. Since the carbon has only 3 bonds, then there is a hydrogen somewhere. And then on the right, it's bonded to something that contains an N, and the other one on the other side is something that contains an O. So this is a chiral center. So actually this molecule has only 1 chiral center. If you look at the other carbons, you will find that they are not bonded to 4 different groups. The decomposition of hydrogen peroxide is catalyzed by iodide ions, and this is the mechanism shown. What is the rate equation for this reaction? How do we get the rate equation from the mechanism? Remember, the rate determining step or what determines the rate is the slow step. Now, if the first step is the slow step, then only reactants in the first step will be included. If the slow step is the second step, then the reactants in both step 1 and step 2 will be included. So if we look at this, it is step 2 that is slow, and we have the IO minus cannot be included because the IO minus is generated in step 1, used up in step 2, so this is actually an intermediate that does not affect the rate equation. We have the H2O2 twice in steps 1 and 2, so it is concentration of H2O2 to the power 2 times the iodide once, so it's iodide to the power 1, so this is the rate equation. Question 8 says the two monomers shown react to form a polymer, which is the repeat unit of the polymer. You need to realize that we can change or rotate these compounds around in order to make it look like the products. So we're trying to see which of these products is the polymer. Okay, if the monomer 2, I rotate it upwards. Monomer 1, I want to make it like something here. So if I do it like this, then like this, so in this case, this is monomer 1 and this is monomer 2. How do we join them together to form a polymer? Remember, we remove OH from the acid, H from the alcohol, and join. So when we join, this is the product. Now this one looks like which of these? So this is the resulting polymer. Turn them around, remove OH from acid, H from alcohol, join together to form the polymer. A partial mechanism of the reaction between ethanoyl chloride and concentrated aqueous ammonia is shown. How many curly arrows are needed to complete the mechanism? So we're reacting ethanoyl chloride with ammonia. How does this react? Remember that ammonia acts as a nucleophile. So the lone pair of electrons on the nitrogen attack the slightly positive carbon, and the electrons between the C and the O go to the slightly negative oxygen, and that gives that intermediate. Then what happens? Then you need the O minus to form a double bond again and release the Cl. So this is the other intermediate, and then we need to change the NH3. So one of the hydrogens is removed so to get that product. So the question is asking how many arrows did we need? Well, actually we needed a total of 6 arrows. What is the IUPAC name for the product? Where is the product? This is the product. What is the name of the product? Remember, if I have C double bond O, N, that's an amide. So this is an amide of what? Of something that has 2 carbons. So this is ethanamide. Okay? How do the boiling temperature and solubility in water of butanoic acid compare with the values for hexane? So we're comparing hexane. This is hexane, something with an alkane with 6 carbons, and butanoic acid. Butanoic acid is something that has a C double bond OOH. Which one would have a higher boiling temperature? Remember, butanoic acid, when it has an OH and a double bond O, so it has permanent dipole-dipole interactions, and it has a hydrogen attached to an electronegative element. So between the molecules, we can have hydrogen bonds. Actually, between each 2 of them, we can have 2 hydrogen bonds. While hexane cannot form hydrogen bonding, so the boiling temperature of butanoic acid is higher. So my answer is C or D. Now, what about solubility in water? Well, if it can form hydrogen bonds, then it can also form hydrogen bonding with water, and therefore it would be very soluble in water. While hexane is not, it cannot form hydrogen bonding with water, so it will not dissolve in water. Which acid would be produced by the hydrolysis of the molecule shown? So what is this molecule? This is actually something that has a cyanide group, C triple bond N. Hydrolysis of this compound would break this bond to form an acid. So this is my product. How do we name this product? Well, we take a look at the longest chain of carbon atoms. So this would be the longest chain, and we need to start counting from the acid group. So this is something that has 4 carbons. So this is butanoic acid, not propanoic or pentanoic. So what are the substituents? Well, on carbon number 2, I have a methyl group. And on carbon number 3, I have a hydroxy. So this is 3-hydroxy, 2-methyl butanoic acid. Which is produced after the polyester shown is hydrolyzed with excess sodium hydroxide. Remember, when I have this ester group, I can either hydrolyze it using aqueous acid or aqueous base. If I use aqueous acid, then the products would have an acid. But this is with aqueous base. That means if I break these bonds, one part will be the dialcohol or the diol, and the other part that was acid, this would now be the sodium salt. So these are actually the products that I get when the polyester is broken down. So which of these is a choice that we have? Benzene 1,4-dicarboxylic acid. We don't get the dicarboxylic acid because this is hydrolysis with base, so it gives the sodium salt, not the acid. And we get the ethane 1,2-diol. We don't get the sodium salt of the alcohol, and we don't get water. The titration curve shown is produced when a base is added to an acid. Which indicators could be used for this titration? Use your data booklet. Okay, we have our data booklet available, and in order to choose the indicator, we need to take a look. Where is the equivalence point, or where is the part where my indicator should change color? So obviously the equivalence point is between about 7 point something to 8 point something. So that is the range that I'm looking for in the data booklet. So when I look at the data booklet, this is the information available. Now, which of these indicators would change within the range that I want, around 8, pH of 8? So obviously you can see that only these 3 will have changing color in the correct range. The others will change color way before the equivalence point. So the indicators that I have are bromothymol blue, phenol red, and phenolphthalein. Which acid and base could produce this curve? Well, how do I know? I look at the pH where we started and the pH where we ended. Now, when we started the pH of about 3, that means, is this a strong acid or a weak acid? This would not be HCl. HCl would have a lower pH than that. So the acid is ethanoic acid. Now, what is the base? The pH is at about 12. So that's a strong base. So that's not ammonia, that's sodium hydroxide. Okay? The structure of maleic acid is shown, which could be the titration curve when sodium hydroxide is added to maleic acid. Okay, obviously maleic acid is an acid that has 2 acid groups. So it has 2 replaceable protons. And that means the graph should have 2 vertical jumps in the pH. So C is wrong, D is wrong, that is too many. Now, are we starting with the acid or are we starting with the base? The question says the titration curve when sodium hydroxide is added to the acid, and that means I'm starting with a low pH, and then I'm going to have 2 equivalence points for the 2 replaceable protons, and I will end with a pH of about 12 because then I would have the excess sodium hydroxide in the solution. What is the IUPAC name for this compound? Well, IUPAC name means we look at the longest chain. What is the longest chain of carbons? So I have a total of 4 carbons. Remember, we start from one end with the acid, but here we have 2 acids, and it would not make a difference whether you start from the left or the right. So this is something that has 4 carbons. So this is bute, not F. So my answer is A or B. Bute-2-ene dioic acid. That is what I have. 4 carbons with, remember, is this an E or a Z? If I have both hydrogens on one side of the double bond and both carboxylic groups on the other side, that means this is a cis, and the cis is the same as Z. So this is Z bute-2-ene dioic acid, which is not a conjugate acid-base pair. What is conjugate acid-base pair? It means I have an acid giving up its proton to become a base. So the NH3 in this case is the acid, and the NH2 minus is the conjugate base because the NH3 has given up a proton. So it is the proton donor. What about in B? Well, if I start with NH4 plus, if it gives up a proton, it changes into NH3, so that is the conjugate base. So yes, both of these choices are conjugate acid-base pairs. What about C? If I'm starting with carbonic acid, you should realize that carbonic acid gives up a proton, but then it changes into HCO3 minus. So it is the HCO3 minus that is the conjugate base, not the CO3 2 minus. So this is the one that is not a conjugate acid-base pair. What is the pH of the solution when 2.15 gram of barium hydroxide is dissolved in 200 centimeter cubed of deionized water? We're given the MR of the barium hydroxide, and we're given that the Kw is 10 to the minus 14. So what do? We have barium hydroxide, 2.15 grams, so I can get the number of moles of the barium hydroxide. That is the number of moles. Then you should realize that each mole of barium hydroxide gives 2 moles of hydroxide ions. And this is what we need in order to get in the end the pH. So what would be the number of moles of hydroxide ions? That's twice what we got for the barium hydroxide. So this is the number of moles of hydroxide ions. But we need concentration. So concentration of hydroxide ions would be this number of moles over the volume that is given to us. Remember, the volume in centimeter cubed, you divide by 1,000, so the volume is 0.2. This gives the concentration of hydroxide ions. But in order to get pH, I need concentration of H plus ions. And we know that H plus times OH minus is 10 to the minus 14. So H plus alone, concentration of H plus is 10 to the minus 14 over the concentration of OH minus. This gives concentration of H plus ions. How do we get pH? Minus log of that, so the pH is 13.1. A Born-Haber cycle for calcium chloride is shown. State the value for the delta H of atomization for calcium. First of all, what do we mean by delta H of atomization? You should know that the standard enthalpy change of atomization is the enthalpy change that takes place when 1 mole of gaseous atoms, so I want to start to form 1 mole of gaseous atoms from its elements in their standard state. So if we're talking about delta H of atomization of calcium, I need to form calcium gas from calcium solid. Where do we have that? Calcium gas formed from calcium solid. That means that is the delta H of atomization for calcium. Calculate the enthalpy change of formation of calcium chloride. How do we do that? What is delta H of formation? It is the enthalpy change that takes place when 1 mole of a compound in its standard state. So I'm trying to form calcium chloride in its standard state. Its standard state is a solid. It's formed from its constituent elements in their standard state. So I need to start from calcium and chlorine. Calcium is a solid, chlorine is a gas. So that means that this, from calcium solid and chlorine gas to form calcium chloride solid, that is the delta H of formation of calcium chloride. Now, how do we calculate that from the Born-Haber cycle? You can see that if I go through all of these arrows, this is the same as going straight from calcium solid chlorine gas to calcium chloride solid. So the delta H of formation is actually the total of all of these arrows, and that comes out to minus 799 kilojoule per mole. Okay, some energy data are shown. Explain why the difference between theoretical and experimental values for lattice energy is very much greater for calcium iodide than for calcium chloride. Remember we said, if the compound is purely ionic, then there should be very little difference between theoretical lattice energy and experimental lattice energy. But if we have a big difference between them, that means that the compound has some covalent character. It's not purely ionic. Now, why is it that calcium iodide has a bigger difference than the calcium chloride? That means that the calcium iodide has more covalent character, and that is because what? What is the difference between the iodide and the chloride? You should realize that iodide ions are larger anion than chloride, so the iodide is more easily polarized, and that means that the calcium iodide will have more covalent character while the calcium chloride is more ionic. Calcium chloride is soluble in water. Complete the energy cycle. So from calcium chloride solid to calcium 2 plus aqueous to Cl minus aqueous, this is delta H of solution. Now, how do we complete this Hess cycle? To form calcium chloride, what can we start with? So we can start from the calcium 2 plus as a gas to Cl minus as a gas. So going to calcium chloride solid, this is what we call delta H lattice. And going to the calcium aqueous, calcium ions aqueous and chloride ions aqueous, this is delta H of hydration. And remember that we have delta H of hydration of 1 calcium and twice the delta H of hydration because we have 2 Cl minus. Now, calculate the enthalpy change using the data and the energy cycle. So this is our energy cycle. The table gives us the lattice energy, the delta H of hydration of calcium ions, and the delta H of hydration of the chloride ions. Of course, looking at the Hess cycle, if we go through delta H lattice plus the delta H of solution, this will give the other delta H's on the right. And that means the delta H of solution is the ones on the right, delta H hydration of calcium plus twice the delta H of hydration of Cl minus the delta H lattice. We get the values from the table and we find that the delta H of solution is minus 77 kilojoule per mole. Question 18 says this question is about the reaction between nitrogen monoxide and oxygen. The results of a series of experiments are shown. The data for the experiments are already plotted. Draw a best fit line on the graph. So of course you just try to join these with a best fit curve. So that's what we have. State how the graph shows that the reaction is not first order with respect to nitrogen monoxide. So this was the graph with respect to nitrogen monoxide. Now, how do we know if this is first order or second order or zero order? Remember, if we're drawing a graph of rate versus concentration, if there is no change in the rate, that means the reaction is zero order. If it is a straight line, then that is first order. And if it is a curve like this, like the one we got, so this is second order. So why is it that this is not first order? Because the graph is not a straight line. If it were a straight line, we would have said that it is first order. Deduce the orders of reaction with respect to NO and O2. Okay, so how do we get this? This was the graph, and the table that we have, we can use it to determine the order with respect to each of them. So from the graph, we've deduced that it's probably second order. Let's look at the table. Where is the concentration of NO doubling in experiment 1 and 2? We are going to choose experiment 1 and 2 because the NO is doubling, but the O2 is the constant. Now what happened to the rate? The rate quadrupled. This is not double, this is quadrupled. So the order with respect to NO is second order. What about oxygen? We need to choose two experiments in which the NO is constant and the O2 is changing. So experiment 2 to experiment 6. The concentration of O2 is half. What is happening to the rate? It's also half. So that is first order. Write the rate equation. How do we write the rate equation? Rate is equal to K times the concentration of NO, second order, that means raised to the power 2. Concentration of oxygen, first order, raised to the power 1. Calculate the rate constant using the data from experiment 1. So we have these data for experiment 1. We want to use it to calculate the rate constant, which is K. So if this is the rate equation, what is K? K is the rate over the concentration of NO to the power 2 times concentration of O2. We have all of these information in the table, the rate, concentration of NO, concentration of O2. Working with these numbers, the K comes out to 8,000. Remember, you must include units. How do we get units? We write out each concentration is mole per decimeter cube. The rate, you already have the units up there. The rate is mole per decimeter cube per second. So mole over decimeter cubed second. Each of the concentrations is mole to, per decimeter cubed. So the concentration of NO is to the power 2 and the concentration of O2 to the power 1. You cancel whatever is the same up and down. This is the overall units for K. Decimeter to the power 6, seconds to the power minus 1, and mole to the power minus 2. The equilibrium constant Kp at this temperature is equal to this. State what this value of the equilibrium constant indicates about the position of equilibrium. Now, this was the equation. This was the expression for Kp, remember the expression for Kp is partial pressure of products to the power of their coefficient over partial pressure of reactants to the power of their coefficient. So this is the Kp. Now, if we say that the Kp is 1.55 times 10 to the power 6, that means the Kp is very high. And that means we have a lot of NO2. And that means the equilibrium favors the product, or the equilibrium is more to the right. So we have more product, so Kp is high. This question is about some bromoalkanes. There are 3 straight chain structural isomers with the molecular formula C5H11Br. Remember, straight chains means the carbons are one after another. We don't have a branch. So, C5H11Br, how many isomers can we draw with a straight chain? Well, either the Br is at the end, or the Br is in the middle, somewhere. So, if we have this, and he wants the skeletal formula, please give him the skeletal formula. What is the number of peaks in the carbon-13 NMR for this compound? Well, let's look. Each of these carbons is a different environment. So actually we will have 5 peaks in the carbon-13 NMR. What if I put the Br on the second carbon? Again, all of these are different environments. So we will also have 5 peaks in the carbon-13 NMR. What about if I put the Br in the middle? Then the part on the left is the same as the part on the right. So actually we will only have 3 different carbon environments. Okay, the high resolution proton NMR spectrum. So this is proton. One of its isomers is shown. Deduce which isomer is present in the sample. What isomers did we have? These are the different isomers. So we are asking which of these belongs to this spectrum. Deduce which isomer is present in the sample, explaining the splitting patterns, chemical shifts, include the name of the isomer and the relative peak areas. Okay. So, looking at the proton NMR, obviously we have only 3 peaks, and that means we're looking at the one that has 3 different proton environments. Again, which of these would have 3 proton environments? It's that last one on the right, in which we have the Br in the middle. So we have the 2 CH3s are one environment, the 2 CH2s are another, and the CH. So, which one is the one at 1 ppm? Well, the one at 1 ppm, first of all, it's the highest. So that will tell you that this is the one with the higher number of carbons. So if we have 6 to 2 to 1, so this is the one that has 6. And you should know that the CH3 here has, each of them has 2 hydrogens on the neighboring carbon. So the CH3 on the right has 2 hydrogens on the next carbon, and the one on the left has 2 hydrogens. So each of them would give a peak that is a triplet. So that peak is a triplet because there is 2 hydrogens on the neighboring carbons. This one is the one for the CH2s. How do I know? Well, this is due to 4 hydrogens, so that would be intermediate height of peak. And each of these hydrogens has how many hydrogens on neighboring carbons? Each of these CH2s has a CH3 on one side and a CH, so it has a total of 4 hydrogens on neighboring carbons, and that's why it is a quintet. And we're left with the hydrogen on the carbon that has the Br. This is a 1 hydrogen, so it will be the lowest peak or shortest peak. And it has how many hydrogens in its neighboring carbons? It has 2 on one side plus 2 on the other. That's a total of 4. So its splitting is a quintet. So this is what we need to explain. And of course, we need to name that isomer. That isomer would be called 3-bromopentane. We have 5 carbons. This is pentane, and this is on the middle, so this is 3-bromopentane. And we said we have 3 different peaks. That is correct. We have 3 proton environments. The highest peak is at the one at 1 ppm. So this is for 2 methyl groups, 6 hydrogens. It has 2 hydrogens on the adjacent carbon, so it is a triplet. The peak at 1.8 is for 2 CH2s, each with 4 hydrogens on the neighboring carbon, so it's a quintet. The peak at 3.8 ppm is for the CHBr. It has 4 neighboring hydrogens, so it is a quintet. Draw the SN2 mechanism for the reaction of 1-bromopropane with hydroxide ions in aqueous solution. So, how do we draw that? We're starting with 1-bromopropane. The lone pair of electrons on the hydroxide ions will attack. This is an SN2, and that means, or that tells me, that the hydroxide attacks at the same time that the Br leaves. This is what we mean by SN2. We realize that the carbon and the Br, the carbon is slightly positive and the Br is slightly negative because bromine is more electronegative than the carbon. And this forms an intermediate in which the Br is trying to leave while the OH is trying to attach itself, and all of this has an extra negative charge. Now, after that, then the Br leaves, and I'm left with the alcohol plus the Br minus with the extra lone pair of electrons. Remember, this is the SN2 mechanism in which we have a primary halogenoalkane attacked by a hydroxyl group. Okay, question 20 says nitrous oxide decomposes at high temperature to form nitrogen and oxygen. Some standard molecular entropy data are shown, so it gives me the molecular entropies for each of these. Calculate the standard entropy change of the system. For this reaction, include a sign and units. So how do we calculate the delta S of a system? You should realize that delta S of a system is the total of the products minus the total of the reactants, and we get the values from the table. This gives a total of plus 74.5 joules per degree per mole. Then the question says the standard enthalpy change of the forward reaction is minus 82. Calculate the entropy change of the surroundings at this temperature. How do we calculate entropy change of surroundings? Delta S of surroundings is what? Is delta minus delta H over T. So the delta S of surroundings will be minus of that negative value. So I end up with a positive value. If we use the enthalpy change as it is with kilojoules, I can then multiply by 1,000 and get it in joules. Then the question says calculate the total entropy change of the reaction at this temperature. So we already have the delta S of the system and we have the delta S of the surrounding. So the total is just the addition of these two, and this comes out to be a positive delta S total. Rate experiments on the decomposition of nitrous oxide produce the following graph. So they have a graph, calculate the activation energy, include the value of the gradient. We know that if we have this kind of equation, the activation energy is minus gradient times R. So we need to get the gradient of this graph. You should know how to get the gradient. It's the difference in the y over the difference over of the x. So this comes out to be a gradient. Of course, this is a negative gradient. Now the energy of activation is minus the gradient times R. So this comes out to be the energy of activation in joules per mole. We divide by 1,000, it gives the kilojoule per mole. Explain whether or not this reaction occurs at this temperature by considering the values. So is this reaction feasible or not? Well, we found out that the delta S total is a positive value, so that means that the reaction is feasible. The activation energy, however, is high, 237 kilojoule per mole. That is high, so the reaction would be slow. Question 21 says hexane 2,5-dione, it means we have two ketones, is a toxic compound formed in the human body if hexane is consumed. Complete the table for the hexane 2,5-dione. Name the organic product formed. So if I have this compound, this is hexane 2,5-dione. When we reflux it with excess acidified potassium dichromate, first of all, what is potassium dichromate? It's an oxidizing agent. It will oxidize alcohol to ketone, but there is no further oxidation of a ketone. So if I put an oxidizing agent on a ketone, there is no reaction. What if I add excess lithium tetrahydroiodoaluminate in dry ether? This is lithium aluminum hydride in dry ether. This is a reducing agent. The reducing agent would react with the ketone to form alcohols. So the new compound would be hexane 2,5-diol. State the observation with hexane 2,5-dione reacts when hexane 2,5-dione reacts with iodine in presence of alkali. Now, reaction of iodine in presence of alkali is a test for something that has a methyl C double bond O. So if we have this, and we do in this compound, we get yellow precipitate of triiodomethane. Hexane 2,5-dione reacts with excess HCN in presence of KCN. Name the type and mechanism of this reaction. Now, this is something that has a ketone. We're reacting it with a cyanide. So this is called nucleophilic addition. The cyanide attacks the carbonyl, and this is the product. Draw the structure of the product. So if I'm starting with hexane 2,5-dione, what would be the product? Each of these double bonds will end up being an OH and a cyanide. Give the observation with 2,4-dinitrophenylhydrazine. Now, this is a ketone, and you should know the ketone or aldehydes react with 2,4-dinitrophenylhydrazine. That is that compound with a benzene ring. And when it reacts, it gives a precipitate. This is a yellow precipitate of the compound with 2,4-dinitrophenylhydrazine. Describe in outline how the product of this reaction may be used to confirm the identity of hexane 2,5-dione. Remember, we said this reaction of 2,4-dinitrophenylhydrazine, it identifies presence of aldehydes or ketones. It can also identify which aldehyde or ketone, because I can take the precipitate and recrystallize it, determine the melting point of the crystals, compare that with the data values, so this can be used to identify the original compound. Alkaline compound is known as tris, is used to make a buffer for biological research. Sketch the low resolution proton NMR. So they want you to show the peaks of the low resolution. That means we don't need to show splitting. Low resolution means no splitting. How many proton environments do we have? Well, we have the 3 OHs, that's one, the 3 CH2s, that's another, and we have the hydrogen of the NH2. So, if you look at the data booklet, you'll find that the NH is at around 1, so we have a peak at around 1, and this is for 2 hydrogens. And then we have a peak at around 2 ppm, that is for the OH of the alcohol, and we have another peak at about 3.5, and that is for the H attached to a carbon that is attached to an OH. So, and then the relative heights of these peaks indicate the relative number of hydrogens. So I have 2 of the NH, I have 3 of the OH, and we have 6 of the CHs. So these are the relative heights of the peaks. This compound is a Bronsted-Lowry base, and its conjugate acid is formed as shown. So when we react it with H+, it gives the acid form. Explain how a mixture of this and its conjugate acid act as buffer solutions when a small amount of acid is added. Remember, any of these act as a buffer solution. How? If we add acid, the base and the conjugate acids are originally present in larger amounts. So when we add a little bit of acid, this causes the equilibrium to shift to the right to use up the acid, but the ratio of concentration of base to acid does not change a lot, so there will be very slight change in the pH, and that's why it acts as a buffer. Write the expression for the Ka. So how do we write Ka? It is concentration of products to the power of their coefficients over concentration of reactants to the power of their coefficients. When hydrochloric acid is added to this compound, the acid salt is formed. The acid salt is a solid that has this formula and contains the conjugate acid of the compound. When 100 grams of the acid salt is mixed with 500 centimeter cubed of 0.2 mole per decimeter cubed of this compound, an alkaline buffer is formed. Calculate the pH of this buffer, assuming that there is no change in volume when the solid is added, and we're given the Ka for the conjugate acid. So, what do we want to get? We want to calculate the pH of the buffer. I have 100 grams of the acid salt. I can get the MR, and that means I can calculate the number of moles, mass over molecular mass, and this gives me the number of moles of the acid salt. I have a volume, so I can get concentration. The volume is 500 centimeter cubed, that means 0.5. I divide by 1,000 decimeter cubed. So this gives the concentration of this compound. And then we have Ka, so I can get pKa. pKa is minus log of the Ka, so this is the pKa. And then I can use this equation. I have the concentration of the tris and the concentration of the acid salt, so I can get the pH is pKa plus log of the ratio of the concentrations, and that comes out to be a pH of 7.27. A solution of chloroethanoic acid is prepared for titration with this compound. 0.015 grams of chloroethanoic acid, and we're given the MR, is dissolved in 1500 centimeter cubed of distilled water. The resulting solution has a pH of this. Calculate the Ka. So we're given the pH and we want the Ka, so I can use it. Use this equation to calculate the Ka. I can get the concentration of H plus ions. Number of moles is mass over molecular mass, so this is the number of moles. The concentration is the N over V, So this is the concentration of the solution. So concentration of H plus is 10 to the minus of the pH. We already have the pH, and that means I can rearrange that equation to get Ka. Okay? A titration curve of this compound with chloroethanoic acid is shown. Explain how this graph shows that it's the tris and its conjugate acid act as a buffer. Now, how do we know from this graph that's a buffer? We look at that region where we have the pH almost constant. So there is very little change in pH when a volume of 4 to 16 centimeter cubed of acid is added. So in that region, the mixture acts as a buffer. Use the graph to estimate the pH of the salt formed when tris is neutralized with chloroethanoic acid. This was the graph. It is neutralized at what pH? Well, that's the middle of that vertical line, so that is pH 6. Last question, suggest a reason why buffers are so important in biological systems. Remember, we need to maintain constant pH so that we have a suitable pH for enzyme activity. If the pH is not suitable, then enzymes become denatured, and that will affect all the reactions in the body. That's the end of this exam. Thank you for listening, and please keep revising.